Okay, so in this video, we are going to discuss matrices. Now, matrices is simply the plural of matrix, and all a matrix is a rectangular array of numbers. So we'll look at a few examples and, along the way, introduce some definitions. So for example, 1, 3, 4, 5 is a matrix. It's a rectangular array of 4 real numbers. 1, negative 9, 10, 1, 0, 2 is another matrix, a rectangular array now of 6 numbers. 3 square root of 2, 4, negative 5, negative 6, 1 is also a matrix. It is a rectangular array of, again, 6 numbers. Well, there is one thing that you can notice is they have different sizes. And so here we say we have a 2 by 2 matrix. The first index represents a number of rows. So this matrix consists of 2 rows and 2 columns. This is called a 2 by 2. So we write 2 times 2, but it's read 2 by 2 matrix. The first index always represents the number of rows. The second index, the number of columns. Well, here is a 2 by 2 matrix. Here, the matrix consists of 2 rows, but now 3 columns. So this is a 2 by 3 matrix. And this matrix consists of 1, 2, 3 rows and 2 columns. So this is a 3 by 2 matrix. And that's it. Well, at least for the size of a matrix. So any matrix is a rectangular array of numbers, and it consists of a certain number of rows and columns. So in general, when we write a m by n matrix, the first index is always the number of rows. So it is the row index. And the second index is always the number of columns. So whenever we say we have an m by n matrix, it is a rectangular array of real numbers that consists of m rows and n columns. Every time we have a new object, we ask, can we perform operations on our new objects? And the answer is yes, but first, let us consider the notion of equality and the notion of entries of a matrix. So suppose that I call this matrix, say, A. So I give it a name. The entries are simply the numbers that are making up the matrix. So the entries of A would be 3, root of 2, 4, negative 5, negative 6, 1. And so we need a good notation to denote or to single out specific entries of a matrix. And if you think of it, we have to specify the row position. Is the entry in the first, second, or third row of the matrix? And then the column position is the entry in the first or in the second column. There are two ways of writing this. We can write the matrix in round brackets. And again, we have to specify a row position and a column position. As always, the first index represents rows, the second columns. So suppose we look at the entry 4. It is found in the second row, first column. So this would be the entry of A21. This is not A21, we leave a space. So when you put round brackets around a matrix, you mean the entry of this matrix in the first index is the row position, so in the second row, first column. So this is entry 4. And we sometimes use, instead of an uppercase A, simply a lowercase a, and we drop the round brackets. We simply write A21, meaning the entry of matrix A in the second row, first column. What if we flipped these two indices? What if we looked for A, now 1, 2? This is the entry in A in the first row, second column. So it's the entry root 2. Once again, we could simply, instead of using round brackets around uppercase A, use lowercase a, 1, 2. Let's look at one more. Let's look at, say, a 3, 1. So the entry in A in row 3, column 1, so we're in the third row, first column, and this is negative 6. Once again, we could use simply lowercase a, 3, 1. So in general, when we write given any given matrix A, when we write A in round brackets and we specify two numbers, two indices. The first is the row index I, the second the column index j. We can again write this as lowercase aij, and this is the entry of A found in the ith row, jth column. So this is a really good notation to specify specific entries of the matrix. Okay, now that we have this notation and we have the idea of a matrix, the first natural question is, what does it take for matrices to be considered equal? Let's look at a few examples and ask ourselves, should we consider these matrices as being equal? Suppose we look at the matrix 1, 2, 3, 4, and the matrix, say, 1, 2, 3, 4, but now let's add a third column, 5, 7. Well, right away, right, when things are equal, they really are exactly identical. They're the same thing. But here we have a 2 by 2 matrix, 2 rows, 2 columns. Here we have a 2 by 3 matrix, 2 rows, 3 columns. So right away, you say, well, even though the first part is the same, this matrix contains an additional column. So for this reason, we don't think of them as being equal, because they don't have the same size. So that's our first criteria. For matrices to be of the same size, for matrices to be equal, they have to have the same size. And now let's look at the entries. What if we looked at the matrix 1, 2, 3, 4, and the matrix 1, 3, 4, 2? Are these equal? They are both 2 by 2 matrices, and they have the same entries, right? 1, 2, 3, 4, 1, 2, 3, 4. But the only problem is the entries are not in the same position. The entry in row 1, column 1 here is 1, and here it's also 1. So far so good. But now the entry in row 1, column 2 is 2 here, and here it's 3. They're not equal. And again, our notion of equality means literally they are identical elements. So the size is not enough. We need to have not just the same elements, the same entries, but the same, and the key word here, corresponding entries. So because the 2 here is in row 1, column 2, the 2 should be here as well. The 3 here is in row 2, column 1. It should be in row 2, column 1 here as well. And the 2 here again, the 4, sorry, is in row 2, column 2. It should also be here in row 2, column 2. So now if we think of these matrices, 1, 2, 3, 4, 1, 2, 3, 4, now those two are equal. They have the same size, they're both 2 by 2, and they have the same corresponding entries. 1 with 1, 2 with 2, 3 with 3, 4 with 4. And this is our notion of equality. Matrices are equal if they have the same size and the same corresponding entries. Let's see how we can write this very concisely. And I'll give you one additional bit of notation. We write R with a superscript of m by n to denote the set of all m by n matrices with real coefficients. As we will see later, it is possible to have slightly weirder coefficients in the matrix, but for now, we will only consider real numbers as our coefficients. So our m by n is the set of all m by n matrices, so m and n are fixed, with real coefficients. So now, suppose we have two matrices. Suppose that A is an m by n matrix. Whoops. M by n. And suppose B is a p by q. And now let's write very concisely our definition of equality. As we have just said, matrices are equal if they have the same size and the same, and the word is very important, corresponding entries. So A equals B as a matrix if and only if, right? This double-headed arrow means if and only if. Well, what does it take for A and B to have the same size? They must have the same number of rows, so M equals P. The same number of columns, N equals Q. And how do we write, very concisely, the same corresponding entries? Well, if you look at the entry in matrix A in the ith row, jth column, and you look at the entry in matrix B in the same position, ith row, jth column, these two have to be equal. And this captures the definition of equality. A and B are equal if and only if they have the same number of rows, the same number of columns, and the same corresponding entries. So wherever you look in A, if you look in row I, column J, and you look at the same position in matrix B, the entries will match. And this captures the statement that A and B are equal as matrices if they have the same size and the same corresponding entries. Let's look at a few more definitions. Special matrices. So the first definition will be a square matrix. So a square matrix obviously will be a square. So it will have the same number of rows as columns. So if we write A belongs to the set of all m by m matrices, A consists of m rows and m columns, we say A is a square matrix. And that's it. So for example, this matrix 1, 2, 3, 4 is a 2 by 2 square matrix. This matrix 1, negative 2, 3, 9, 0, 1, 1, 1, 7 is a 3 by 3 square matrix. 3 rows, 3 columns, and so on. So it's a pretty obvious definition, right? The matrix is called a square matrix if it is a square, if the number of rows matches the number of columns. Let's look at a few more definitions. So again, we're going to look here at square matrices. So if A is a square matrix, we say A is upper triangular. So we say that A is upper triangular if, quite simply, the entries above, oh, sorry, I should define something before. I was going to say the main diagonal, but we need to define that first. Let me just skip ahead here, and then we'll go back to this. So when you have a square matrix, the entries where the same number with the same row index as the column index are called the main diagonal entries. So if you look here, it's a very simple definition. This is the entry 1, 1, row 1, column 1. This is the entry 2, 2, row 2, column 2. This is the entry 1, 1, row 1, column 1. The entry 2, 2, row 2, column 2. The entry 3, 3, row 3, column 3. Now those entries are set to form the main diagonal of the matrix. Let me just write this here. So the entries A11, A22, A33, up to, if A is an m by m, we end up with the mm entries, so A, M, M. So these entries form the main diagonal of matrix A. And again, it's a pretty obvious definition because as you can see visually, they really look like the diagonal of the square matrix. So the entries A11, A22, A33 through AMM form the main diagonal of A, and now we can define what an upper triangular matrix is. So A is upper triangular if the entries below the main diagonal are all zeros. So the entries on the diagonal can be anything, and above can also be anything, but the entries below the main diagonal have to be zeros. Let's look at a few examples. Suppose we take 1, 2, 3. Here's your diagonal, can be anything you want. Here's what's above, but what's below has to be 0. So this would be a 2 by 2 upper triangular matrix. Let's consider it 3 by 3. Once again, the main diagonal can be anything you want. So suppose it's root 3 pi negative 6. The entries above can be also anything you want, say 8, 4 minus 1. But the three entries below have to be zeros. So this would be a 3 by 3 upper triangular matrix. And you could look at 4 by 4 and so on. So obviously, we have the analog definition of a lower triangular matrix. And you can see again visually why we use the word triangular, because if you look at the entries on the main diagonal and above, it really does form a triangle of values. And we say upper because the triangle is on top, is above the 0 entries. So here's one of the definition as we have just said for a lower triangular matrix. So we say that A is lower triangular if the entries above the main diagonal are 0. Let's look at, again, two very simple examples. So what's on the diagonal can be anything we want. Let's go with 1, 2. What is below can be anything we want, 3. But the entries above the main diagonal have to be zeros. This entry here would have to be 0. Let's go with a 3 by 3 upper triangular matrix. On the diagonal, we can have anything we want. So 6, 8, negative 9. Below, also anything we want. So 4, 3, 1. But now that the entries above have to be zeros. And you can see once again, if you look at the entries on the diagonal and the entries below, they form a triangle of entries. And that's why it's called a lower triangular matrix. Let's look at one last definition for a square matrix, and that is a diagonal matrix. And that's at the same time upper triangular and lower triangular. So everything below the main diagonal is 0, and everything above the main diagonal is 0, so all you have are possibly non-zero entries on the main diagonal. So again, A was a square matrix, so we say that A, which was by assumption an M by M matrix, so we say that A is diagonal if the entries above and below the main diagonal are equal to 0. Let's look at a few simple examples, and we'll see how we can write this very concisely using our notation for the entries of a matrix. So A is a diagonal matrix if the entries above and below the main diagonal are zeros. So on a diagonal we can have anything we want, but what's below and above has to be 0. So here's a 2 by 2 diagonal matrix. Now the entries on the main diagonal can also be zeros. For example, 9, 0, negative 8. So you can have 0 entries on the diagonal, but what's above and below all have to be 0. So this is a 2 by 2 diagonal matrix. This is a 3 by 3 diagonal matrix, and so on. So when everything off the main diagonal is 0, you have what's called a diagonal matrix. And just to use here our entry notation, let's see how we can write this really concisely. If you think of it, the entries on the diagonal are the ones with the same row and column index. This is the entry 1, 1, the entry 2, 2, the entry 3, 3. So let's look at this. Above and below the main diagonal are zeros. So if you say matrix A, the entry in the ith row, jth column, if I is different than j, if the row index is not the column index, then you are off the main diagonal, right? The only way to be on the main diagonal is if the row index equals the column index, A11, A22, A33. So if you want to say that the entries of the main diagonal are zeros, we simply have to say that Aij is equal to 0 if I is simply different from j. If I and j are different, you are off the main diagonal. So if that's the case, whenever I and j are different, that Aij is 0, every entry off the main diagonal is 0, and the entries on the main diagonal can be anything you want. This concludes our basic introduction of matrices. In our next video, we are going to look at what kind of operations can we perform on matrices. Can we add them? Can we multiply them by real numbers? Can we multiply them together? And this will be the topic of our next video.